How much time are you going to speak?
I think it's an hour, isn't it?
What?
Is it an hour for the call?
Okay, then maybe when the time approaches to 10, I'll give you some signs.
I've got, yeah. Oh, is that that? Yeah. Oh, there's two.
This is for me
Okay.
when I'm presenting.
Ah.
And at the end, I'm going to give you this bracket.
I might hear it.
Is it starting now? Maybe we should close the doors.
Yes, any moment now. Very important message. Listen. So I am now presenting you Andrew Turner from New Zealand, who is going to talk about the FreeBSD on IRM64. So let's greet him.
Thank you. It's a sort of a, even though it says porting FreeBSD to AR64, it's more of a, what do you need to know if you're trying to port your software there, or working on device drivers, or what do you need to know about ARM64? So a wee bit about me. I'm a FreeBSD source committer. I've been doing this ARM-related things for FreeBSD for 5 years, and as a committer in a few years before that. I originally got into FreeBSD on ARM with the OpenMoko cell phones a few years ago. Sort of ran it on there, sort of successfully. As of about a year ago, I've been working as a freelance software engineer, and so a lot of the ARM64 work is part of this, and is paid for by the FreeBSD Foundation. So I'm just going to give you a wee bit of an overview of ARMv8, because I'm assuming most people here haven't quite got into it as deeply as I have, and really having to understand a lot of low-level details. So we'll start off with early boot, and there's two modes in an ARM. There's a secure mode where you run things like, say, for example, your DRM if you're on a cell phone and you want to watch Netflix, and there's a non-secure mode. So these are just there's a wee bit of trusted code. When I say trusted, I mean trusted by the vendor. And there's the untrusted by the vendor code, which is where FreeBSD runs, because that's where your most operating system code works. And there's messages, there's ways of passing data between them. So most of what we were interested in here is running on the non-secure side. because we're untrusted. There's 4 exception levels. These are these are where your code will run. So the chip firmware, the L3, that runs, and that's the secure side. And the other 3 levels are hypervisor. Well, I say Beehive would live there, but generally it would be a little bit of stub code would live there, which would then call back into the kernel. Or Zen lives there, and then we've got the kernel and user space. So as the number gets smaller, you get fewer privileges. And yeah, so L0, 1 and 2 is on the non-secure side. You don't get a hypervisor on the secure side, so you only get 3, 1, 0. And 3, L3 is on the secure. So execution, we can run, well, ARMv8A, which is what most chips are at the moment, have a 64-bit mode, and there's an optional 32-bit mode. The ARM have given it interesting names, which if you look on the original port, or when they first submitted a Linux port to Linus, didn't seem to like them. If you have a look at that one day, it's an interesting. He seems to think there's something in the water in Cambridge. So the only way you can possibly switch between these 2 modes is by changing exception level. So if you're running, and as you move, you can only change from 64-bit to 32-bit by moving to a lower exception level. So therefore you have to have, if you wanted to run, if you have a 32-bit kernel, you can only run a 32-bit user space. If you have a 64-bit kernel, you could run either, assuming your hardware supports 32-bit. Moving down an exception level, you can move from 64 to 32, and the only way to return back to 64 is by moving back up an exception level. So there's no interworking between the 2 at all, which is one thing, I suppose. It's useful for not having to worry if you've got suddenly having pointers change size. So there's 3 instruction sets that only 3 we're interested in. I'm not sure. I think there was Giselle in earlier ARM. I think they might have got. I'm not entirely sure if they have that or not. So they've renamed them as well. So A64 is the 64-bit instruction set. A32 is if you've come from before. This is what they meant with this is the original ARM instruction set. And T32 is thumb2. And they've added some more, so it's basically ARMv7 plus some more instructions. Some things around crypto, so you can do CRC, and you can do things like CRC 32 instructions, AES I think maybe in there. There's a lot of registers. There's 31, which works out well because it turns out in ARCH32 there's also 31 registers. They're just, as you move between different modes of operation execution, they bank the registers, so things like the stack pointer is different for an interrupt as it would be for the kernel. So these are X0 to X30, and X30 is the link register, so that gets updated automatically on if you call into a function. And the bottom 32 bits are mapped to our 32-bit registers, so it's the X means 64-bit and W means 32. And then the program counter, stack pointer are special, and there's a 0 register, which you can write to as much as you like, and always read 0. And then there's more floating point registers, so long double on ARM is 128 bits. And each the floating point registers is split into 2 64-bit registers, and those are split into, each of those is split into 2 32-bit, and maybe those are also split into 2 16-bit on some implementations. So that's basically if you're wanting to support floats and doubles. So ABI is simple. If you've looked at ARM before, it's similar. It's just using more of the registers. So just put passing arguments in registers until they until you've unless you use more than 8. And x8s will be a bit special if you're returning a strut. Then there's caller and callee saved. If you're really interested in this, there's the ABI documentation you can look through, and they've got all the various rules about this. There's two quite distinct virtual memory ranges. There's the low range, which is starting at address 0, and which we use for user space. And there's a high range, which finishes at the top of memory, which we use for the kernel. And there's a large gap in the middle, which is unusable on purpose. So we can't possibly accidentally add 1 to an address and get into the kernel, which you could on 32-bit operating systems, where if you've got say a 2 gig, 1 gig kernel, 3 gig user space, you haven't got any gap between the two. They support up to each range could have up to 48 bits of virtual address space, but because it was easier when I did the work, we've only got 39 at the moment. We're working on improving this now. And we use 4 levels page table. So it's very similar to AMD 64 if you worked with the virtual memory there with the page table layout. The reason for 39 bits is that it uses 3 page tables, and that was the first thing I got working, so I left it at that. This is something that people find odd, is we can select the page size in software. So the default we use is 4K, as the standard, but there is a way when you're turning on the menu, you can set you could set a 16 or 64K page as the base page size if the hardware supports it. So most hardware may only support 4 or 64K. You may need to take this into account in user space, but hopefully not, because as there's a quote on IRC a few days ago saying one cannot expect to relocate binaries differently depending on the backing page size. The hope is that it's been set up, the API set up well to handle this. So if you haven't worked with ARM before, this is quite confusing for people coming in. Naming is difficult. They've fixed it recently with Cortex. So the 2 pieces of information you need to know nowadays is ARMv something or other is the architecture. So this is ARMv8 is the 8th edition of this, which is the instruction. It's instruction set. They've got things like the cache and things like some of the peripherals. So ARMv8 specifies one of 2 interrupt controllers and the timer. So the timer is now required to be as part of the architecture, which was an optional in ARMv7. And then there's the implementation. So there's Cortex-A something or other as ARM's implementation. But you could, as a company, buy a license to write your own implementation. You could take these various different licenses. So you could take their existing one and tweak it. You can design your own from scratch. So yeah, as I was saying, there's either use their own or they'll design one themselves. So the 3 designs so far, from ARM, are the A53, which is generally a mobile. It's quite a low end. I think it's in order 3. I think it's quite a short pipeline. I think it's about. There's the A57, which was the high end or higher end out of order. So these 2 were designed about the same time. And then there's ACD2, which is a rework. It's a slightly faster, it's reworked a wee bit to be lower power and things like that. That's just coming out now. So you'll find, they'll just find these occasionally in different SoCs. And then there's other custom designs you can get. So Cavium has their own design. I'm not entirely sure if Apple's is exactly how much of it is custom versus tweaked designs. Okay, so that's sort of the brief overview of ARM. I'm now going to get into quite some low-level details. And yes, I know it's morning and we have just had coffee, so it should be fine. I'll start off easy. Device model. So we generally assume at the moment we're booting off UEFI, and that is going to provide us hopefully with either the device tree through the flattened device tree spec, or ACPI tables, and unfortunately it is ACPI. So you may need to support, if you're writing a device driver for ARM, you may need to support both. Each of them will be, they have their own ways of finding which resources you use, and luckily you'll only ever get one, so you don't have to worry about handling that you may have attached on one bus but not the other. You will only ever get one bus. Memory. So when I say normal memory, I mean something backed by RAM. It's relaxed, so that means things happen out of order. It's not as relaxed as alpha. Dependent nodes will be in order. So you are safe in assuming that. So if you're writing a single-threaded application, you can ignore most of this. It's fine. It doesn't really matter in the single-threaded world what order things happen in. The reason for it being relaxed is that's how they get low power. So an example, x equals 1, y equals 2. This could happen, x could be stored first, y could be stored second, or it could be y stored first, x is stored second. You don't know. Even if this is the assembler example, this is doing store x0 into the address pointed at x1. And the second this is x2 storing, register x2 stored at the memory that's pointed at by x3. We don't know what order the hardware will decide to execute those two instructions in. And even if it does execute them in order, then it may reorder them in the memory buffer, the buffer out towards the cache. So just because it may group, if you're doing other writes, may just group them and write them all in as a cache sign. I think this is problematic for a lot of software if it's coming from assuming certain ordering semantics, which may not be true. So hopefully this code will actually execute in order. Given that, I'm doing in the C code, I'm loading data from what's pointed at X and storing it into Y. You can see there's a dependency there that we need to have read from X before we can store in Y, and the assembler is the same. It's saying X1. There's a dependency between the load and the store. X1 is read and then it's written. You've got to have read X1 before you can write it out again. There's other solutions. So if you're trying to write code and you need to know this data has been written before this other piece of data, there's two options. You've got a full barrier or you've got a half barrier. The half barriers are very much aligned with C11 semantics. So this is full barrier example. We need to know that the store of x into x1 happens first. Yes, so this is a full barrier. So DSB is a data store barrier, I think it is. And ISH so it's just saying I'm going to write to an shareable memory, which is the magic type of memory that ARM uses. So it means that the first store happens, and then we only at the point at which all of those stores, any prior those stores have completed, or any later loads and stores be started. So that's useful if, say, if you're wanting to signal across threads. Half barriers. They only have they have store release semantics. So I can say I'm writing x0 to x1. I've got a half barrier, so that's what the SDLR is. That will mean that the prior loads and stores will have completed, but later memory access may be moved beforehand. So that's slightly more efficient if you're not caring about what happens after an instruction, after an operation happens. Yeah, well, why should you care? Because it's threads. Just to make it, threads are hard, and just to make them even harder, we'll add atomics. So synchronization is difficult. So I have two threads here. Thread 1 is sitting in a busy loop, waiting for x to be non-zero. And then it will print the value of y. So this is just something, if you're doing high-performance code, you may use something like this, where if you've profiled and you found that the overhead of locking is too much, because if this was happening, if you're doing this happening this quick enough, then you may want to run it this way. So what we do is we'll set y to 2. And then just because I absolutely must, even if I can't remember the exact semantics of C as to whether volatile stops things happening, I've decided I'll put in a memory barrier, which is a C level memory barrier, because that's just stopping any C level, any instruction level reordering. There's no instruction there at all generated. And then you'll set y to 1. And then we run this, and we find sometimes it's 0, sometimes it prints 2. This is because even though we've got the instruction stream has, y is being set to 2, and then it's written it out, then x is set to 1 has been written out. And then we read x is not 0, and we read y, and we find that it turns out that y was still in some buffer somewhere and hasn't actually got to the cache yet, and hasn't, it's been, or the instructions have been reordered, and so y hasn't even the store to y hasn't even happened yet. So hopefully, if you're doing anything with threads, you'll be locking or using semaphores, or the C11, I think C++11 have got a memory model now. So this memory model is the ARM instructions are designed to fit the C11 and C++11 memory model well. So they are designed to be right on the point of where how weak and very strong they are as required by this memory model for atomic functions in C11 and C++11. And it turns out because these memory models were based on prior architectures, and FreeBSD came up with our own atomic functions based on the same architectures. The FreeBSD atomic functions also fit the ARM instructions very well. So I think that means that we could probably argue that the FreeBSD atomic atomic functions are very similar to. You could possibly just replace them with C11 atomics in the kernel. So there's a few. I think these are C11 functions. Atomic load and store. Atomic thread is basically a memory barrier saying anything, a DSB, so it's a full memory barrier. And hopefully this code is actually correct. So I've replaced so if you remember back in this code, we're looking for check X is non-zero in thread 1 and then printing Y. This time we're doing explicit memory load where we've got acquire semantics. So anything that is after this code that load acquire, this load can only be executed after this load has finished. So this is the opposite of the store release. So it's stopping the load of Y for the printf that can't possibly happen before the while loop is completed. And then thread 2 is setting Y to 2 and then doing a store release. So that means that the store to Y, the store to Y is guaranteed. It must have happened before the atomic store the store release is executed. So this is low-level synchronization. It's only useful that the pthread should handle this all for you if you're using threads or if you're using mutexes or semaphores. This is if you're trying to do something really low-level. I have a question for Colin. So the question is, over multiple CPUs, what does it mean for a store to complete? It means that there is actually a definition in the ARM reference manual where I'll paraphrase from memory it's to do with whether or not other execution units can observe the store. So I think we can just, I take that as can the other CPUs, has it hit cache, and at which point the cache coherency will kick in and the other CPUs will know, then when they do a read from memory, they'll go to the cache and they'll find that they can read it from the other, they'll snoop it from the other cache and put it in, or have been written out to memory or something. Yeah. So it's basically at the point of cache coherency. It also means that so therefore that also would mean the instruction must have executed for it to, you can't possibly have not executed the instruction to have a store and then have it complete. Obviously you've got to have executed the store instruction before you've tried to do anything later that may have a dependency on that. So for example, the load or another store. If you're interested, I can point you at documentation which goes into quite difficult to read. I've heard rumours that there might be easier to read, easier to understand documentation inside of ARM, but because lawyers, they had to rewrite it. Yes, this is difficult. If threads are difficult, atomics just make them make them worse. If you're really interested in atomic operations, I can point you at a talk by someone from Microsoft who, so over a few hours, he talks all about atomics and memory model in C, and how now more about the fact that there is now a memory model in C, and sort of the history of how they got to there, and he goes into a lot more detail on various different atomics. I don't claim to be an expert. I know about the low level bits about how they're implemented. I don't necessarily know about all the atomic functions you can see C11. Luckily, if you're writing a device driver, we have a different, so this was all normal memory. That's before. That was writing out to RAM. It's designed to be reordered. It's designed, devices, we can map devices slightly differently in that we have a wee bit more, we can select a strongly ordered memory model with devices so that the default is everything is in order. We only complete a write will be something will be written to a device. It will signal back saying I have received this write, and that will only happen. The response will happen when the device receives it, the write request, and if you do two writes to the device, then they'll stay in the same order. Two writes from a single CPU, they'll stay in the same order, and they won't. So basically, none of these three options here I've got are enabled. We then may enable. We can say, well, we are fine with knowing we've written to this device. The memory, the write is on the bus going out to the device, but it's fine to send a signal back. And this is the memory model of device memory on FreeBSD on ARMv6 and AV7. That's a wee bit early. We know the write's going to hit the bus, the device in the end. And it's just a hint to the architecture, so the hardware saying it could do this, it doesn't have to. And if we really liked, we could say, well, we can actually handle reordering of writes out to the device. You do realise then you're going to have to put in, if you can't handle certain reordering, you're going to have to put in memory barriers, but if you've got hardware that will support writing to, if you're doing writing to multiple registers, it doesn't really matter the order. Some hardware is like this. We could possibly turn on reordering, and then there's gathering. So writing, if you were writing to the same to a register twice. Could it just say, well, you write it, just do the second write? And somehow we may support this. I don't think there's any way in FreeBSD of us telling a device driver telling the kernel that it would support any of these. So if anyone has any ideas on how we could do this, I'd like to be able to have the device, I'd like to be able to have a weaker device memory model when it makes sense. Because things like PCIe, ARM suggests don't turn any of these on. So that at the moment our default is all of these are off. And we can only, so there's only four options. So we could turn these on only in the order I've listed them here. So we could turn on early write, and we couldn't have gathering but not reordering, for example. It's not an option. And caching. So there's two levels of cache, and data and instruction cache is split. Data is obviously read and write access, instruction is execution, so it's only ever going to be read. But this is only at level 1. At level 2, it's combined data and instruction. Your hardware may have a level 3, but that's outside the architecture. So you're going to have to then handle, if you need to handle level 3, we're going to have a think about, figure out how to do that. Level 3 is, I don't think we've got any hardware yet which supports it, and it's a future project if we do finally get some.
Actually, quick question. Is the L1 instruction and data cache, are those coherent? In that if you write to the...
No, I've got the slide up. So the question was about coherency between instruction and data cache, but I'll talk about that soon. So only normal memory with cacheable attribute. So you could ask for uncacheable memory if you really like to, and that will mean we couldn't possibly cache it. It will go straight out to RAM. You don't normally need to handle the data cache in user space unless you're doing something weird. And there are APIs we could handle this, because normally you only care about it for you may need to care if you're doing some sort of user space driver, which you've directly memory mapped dev mem or something, and then you should do it uncached anyway, and the kernel should make it normal memory, device memory. You only need to handle the data cache in a few places in the kernel. Mostly that's hidden behind the various APIs, and most of the places we actually have to handle it is to implement the APIs. The kernel doesn't necessarily need to know. It's only things like DMA where you care about if you're DMAing something on a cache incoherent. If your DMA is not cache coherent, if your DMA engine, sorry. So this answering John Mark's question is because we've got a split data and instruction cache, you need to handle this. They're not cache coherent. They may not even be the same. So the data cache is going to have different. It's going to be as virtually tagged, I think. And instruction cache may be. It's got a few options on tagging and indexing, depending on your exact architecture and what your requirements are. So there may not even be very similar. The caches may be completely different designs. You're going to need to handle this if you're writing a JIT, or if you're loading shared objects. The kernel should handle that for you, as long as you're not doing it yourself. If you're not writing your own elf parser, you're fine. If you're just using RTLD, the runtime linker. If you do need it, right? If you do need, while writing a JIT, you're going to need to use something like clear cache just to make sure the data you've flushed out anything from the data cache and validated anything in the instruction cache. And that should just work, I'd hope. DMA, because the DMA engine is outside the architecture, that means that any SoC vendor may implement their own engine. It may or may not be cache coherent. So the Cavium DMA engine, for example, is cache coherent. So you can just we can make things like the sync operations no ops, because you've written out to the cache, as long as that'll be a memory barrier, sorry. As long as you've written everything out to cache, and then the DMA engine tries to read it, it's fine. It will get it back in from the cache. You should call DMA, bus DMA map sync. If your driver's not doing this already, you've probably got, you've broken, it's entirely broken. There are, as we try to make, with the device memory, the DMA is one of these big problems, with like the dice. I mean, we would like to make it as lazy as possible and relaxed as possible, because that's where we can get the performance improvements in ARM. So I'm sure we could, we've got various people that have had issues with this and on RMVC, and I'm sure we could, they'd like to talk to people if they've got ideas on how to make, improve, make it better. So any questions? Otherwise I have a demo of actually running FreeBSD on a box in Austin. No questions? Okay. Yeah. So this is this is one of the now. This is actually a Linux machine running in a data center in Austin, thanks to Lenaro who loaned it to me. But it's running. So it's running KVM, or it's running Linux, so I can get KVM. Do I need to increase the font on this? Is it readable? So this is real hardware. This is I think it's an HP Moonshot, which is an Applied Micro X-Gene silicon, their own design CPU with 8 cores. So I've got, is it because it's KVM, so this is running QEMU with various options. This is almost an identical copy of what is emailed in the snapshot email every week that the release engineers do, except for there is this extra option, enable KVM. That just means talk to the KVM the Linux equivalent of Beehive. And so you see, boots into your EFI, and we'll boot. This is now loader, so if I hit space, say we're in the standard loader prompt. Standard boot. And I should have, so we've got a virtual network. So this all works fine. We can, we're just trying to get more people, people interested in playing with it. I've got, I have a second, we've got hardware we can carry around. I have a small board that runs FreeBSD. This is things like this, which is the exact same image I could write to this server running. This is only single core on here, but it's a high-end it's a high-end server run on this board, which is a low-end mobile SoC designed for putting into a mobile phone. This is the high keyboard. Which will run, it's all, because we've designed for generic from begin with, it's all the same. So, does anyone want me to run something on here to show that it's actually a live system? Or last time people asked me for DH, in BSDCon people asked for DH client, and that didn't work, so I have this set up beforehand, it works. This virtual machine has one because there's some issues with multiple core on this hardware, which it's only on this hardware I'm seeing it.
So do things like hardware PMC work?
So do things like hardware PMC work? Yes. I don't know if it will work on a virtual machine or not. Okay. I can't actually see the bottom of my screen, so I have to. What was the command for hardware PMC? I can't remember. PMC stat, this one. Yeah. Okay, so now we've run into a bug in QEMU where I've lost access to this terminal. Luckily I have SSH access. Someone's going to remind me that I haven't used PMC stat in a while, so someone's have to remind me the options. Pardon? John Mark's looking that for me.
System-wide sampling, so PMC sat dash capital O
So,
dash capital O
capital O.
and space like sample.stat.
Actually, and you mind putting it in top mode? Just capital T instead of capital T, so the capital O.
So much.
With minus capital T instead of minus capital O.
So capital T.
So yeah, backspace up to capital T.
Minus capital T and then what? Dash capital S instructions. Okay, just
No, I'm sure there's a way of listing them all, but it's possible it's not going to work because this is a virtual machine. I don't know if no, I don't think it will work. The PMU is the hardware in it for PMC on ARM.
So in terms of real-world hardware, where are you currently working?
So real world, we currently run on, so this is the high-key board, which if you go 96boards.org, it's on there. And the KVM hardware, so the ThunderX, there might be, I'm not entirely sure if we've got, if they're shipping anything yet, though, you can buy. Unless, except for the customer, they've got some demo boards that you could get hold of somehow. If you're, yeah.
So using the KVM stuff, how many cores do you currently support?
So KVM cores we support, in head we support 48, which is they've got a 48 core board. And there's work on supporting 96. So, and they have a dual chip configuration where you can run, so you run both, you can run the 48 cores in each chip.
And what kind of scaling performance are you seeing?
Performance, we haven't looked into too far yet. We have some hardware that's current, from KVM which is currently having issues, so we can't look into that easily.
What's the TDP on the chips?
TDP, sorry?
The power rating?
I'm not entirely sure what the power rating on the KVM chips are. I know because this is a mobile chip, it's low. I run it, I've got, you can run off 2 amp, and it's probably got at least 1 amp spare. Yep. D-message? Anything in particular? If I pipe it to something. So you do get a lot of VirtIO because the way QEMU builds the device tree, and it just automatic in QEMU, so it puts in all these VirtIO devices for you. So you can see this one's trying to do ACPI and failing. You'll get that on any FTT, if you're booting FTT at all. So OF3 bus 0 is the root of the folder, the flattened device tree. And lots of these. So Yeah, we've got a network and a block disk, so and a standard ARM UART, a standard ARM interrupt controller. PSCI is a way of talking to the firmware to do things like power management, so reboot, turning on and off CPUs. So we use this for SMP. And then we have a CPU driver for each CPU we find. Generic timer is just it says ARMv7 generic timer, but it's the same interface, well, very similar interface.
So speaking of power management, are you actually currently doing real-time throttling to fit within a certain thermal envelope?
So question is on power management, and we're not doing any. There's no power management. There's talk on power management, and it would be a nice thing. Yeah.
Useless without it.
If people want to talk to me about power management, I can. I'm sure we can find someone that will be interested in working on it. So it's standard, fairly standard boot. So the idea is, because it's UEFI, so this part should feel similar to someone coming from an Intel world, where you've got a standard BIOS or UEFI, and you've got the standard loader, so it's all the same. And booting, it's coming up with going into FreeBSD. There'll be some minor differences, and if there's something people really want, we can easily change things if it's a useful option. Or maybe it's the way we were doing it before wasn't necessarily the best, and now we've got a slightly different way of doing it. Any further questions? Or? No? No, thank you.
Wait. Anyway, so now we have a present for Andrew, which is Swedish bread, which he can, if something doesn't work, he can, or he can eat it eventually. Here, right?